Anyone who has ever peered into a glass of water is familiar with the idea that light changes direction as it passes from one medium to another, producing strange optical illusions. This effect, known as refraction, has baffled and excited humans in equal measure and has inspired many an attempt to understand the fundamental properties of light and matter. In this short video, I would like to tell you about the pioneering work of Pierre de Fermat, who discovered that light is the laziest object in the universe, always preferring to take the path that minimises the amount of time spent travelling between 2 points. But perhaps what is even more exciting is that Fermat's principle lies at the heart of one of the most successful scientific theories ever created, quantum electrodynamics. So why is light so lazy? And how does Fermat's principle connect with our modern formulation of quantum electrodynamics? So if you're ready for the ride, let's get started. Consider a beam of light passing from air into water. We can define the angle of the incident and refracted beam in relation to a dashed line, known as the normal, which is perpendicular to the surface of the water. If we then label θ1 as the angle of incidence and θ2 as the angle of refraction, the question we wish to answer is this: what is the relationship between θ1 and θ2? If the answer doesn't immediately jump out at you, don't worry, you're not alone. In fact, this question puzzled our ancient ancestors for thousands of years. It is, however, one of the few places in Greek physics that it is actually possible to find experimental data written down. In 140 CE, Claudius Ptolemy made a list of the angles of incidence and refraction for light passing into water, which you can see written down in the table. Writing information in a table may seem like a trivial step forwards in our attempt to understand the properties of refraction, but this is one of the most important steps in the development of a physical law. First we observe an effect, then we measure it and list it in a table, and then we try to find the rule by which one thing can be connected with another. So what is the relationship between θ1 and θ2? Often, a helpful way of spotting a relationship between two quantities is to plot a graph. So let's go ahead and plot θ1 on the y-axis and θ2 on the x-axis. Then we find a characteristic curve when we plot the data from Ptolemy's table. So what kind of curve is this? Well, the answer to that question had to wait over 1,000 years until 1621, when Wilbrord's Snell found a remarkable connection between the angle of incidence and angle of refraction. To understand Snell's law, we first need to understand some basic trigonometry. A right-angled triangle is a triangle in which one of the angles is 90 degrees. If we then label the angle on the left-hand side as θ, we can then label the different sides of the triangle in relation to this angle. Firstly, the longest side of a right-angled triangle is called the hypotenuse. Next, the side of the triangle adjacent to the angle θ is called the adjacent side. And finally, the side opposite the angle is rather helpfully referred to as the opposite side. Armed with these labels, we can now define sine of θ as being equal to the ratio of the opposite side of the triangle to the hypotenuse. Now it's worth pointing out a few things. Firstly, we see that as the angle θ gets smaller and smaller, the length of the opposite side of the triangle will also get smaller and smaller, and therefore sine of θ will approach 0. Likewise, as θ tends to 90 degrees, the length of the opposite side will grow, and the ratio of opposite to hypotenuse will tend to 1. We can see this a bit more clearly by plotting a graph. Imagine we have a triangle with hypotenuse equal to 1. Then as we increase the angle θ, we can plot how sine of θ changes. We see that when θ equals 90, sine of 90 equals 1, as previously mentioned. When θ equals 180, we see that the opposite side of our triangle has reduced to 0 length, and therefore sine of 180 equals 0. When θ equals 270, we see that the graph reaches a minimum value of -1, and therefore sine of 270 equals -1. And finally, when θ equals 360, the opposite side of the triangle has again reduced to 0, and therefore sine of 360 equals 0. And so we see that the sine function varies smoothly between +1 and -1 over a cycle of 360 degrees. So what does this have to do with refraction? Well, Snell's great insight was to recognise that instead of comparing the angle of incidence θ1 with the angle of refraction θ2, We should instead compare the sine of the angle of incidence with the sine of the angle of refraction. If we calculate the sines of these angles, then we find the following expressions in the table. Now, this might not immediately strike you as an improvement. However, as before, perhaps if we plot these results on a graph, the relationship may become a bit clearer. More specifically, if you plot the sine of the angle of incidence on the y-axis and the sine of the angle of refraction on the x-axis, then you get a straight line that passes through the origin. In other words, the sine of the angle of incidence is directly proportional to the sine of the angle of refraction, and therefore we can introduce a constant of proportionality n and write that sine theta 1 equals n times sine theta 2. If we then rearrange for n, we see that we can determine n by finding the gradient of our graph. Snell discovered that this relationship holds for a whole range of transparent materials, with each different material being characterized by a different value of n. For example, for water, n is approximately 1.33, whereas for glass, n is approximately 1.5. Knowing the value of n for a particular material allows you to then use Snell's law to predict the angle of refraction for a given angle of incidence. But what does n actually represent, and how can we explain it? As physicists, we want more than just a relationship. We want to understand where the relationship comes from and why it is true. Well, the good news is that in 1650, the French mathematician Pierre de Fermat provided a beautiful insight into the properties of light by suggesting that light obeys the principle of least time. As with many great ideas, it's rather simple to state. According to Fermat, when light moves from one point to another, it will take the path of shortest time rather than the path of shortest distance. To illustrate Fermat's idea, consider the following classic example. Imagine you're at the seaside standing on the beach at some location A, when suddenly you notice someone in distress in the water at location B. The question is, how do you get from A to B in the shortest possible time, given that you can run faster on sand than you can swim in water? Well, the first thing to appreciate is it would be silly to run straight towards the sea, since then you would have to travel a longer distance in the water, and we've just established that you would travel a lot slower in water than on the sand. So you might think it best to run further across the sand to minimise the distance travelled in the water, although you need to be careful not to overshoot. In reality, the path of least time will be somewhere in between the paths shown, with the exact path depending on the exact ratio of the speed on sand compared to the speed in water. It was Fermat who considered the possibility that, much like the lifesaver who takes the path of least time to reach the person in the water, light might also take the path of least time when travelling between 2 points. To see how this works in detail, let's now imagine that the red arrows describe a ray of light passing from air into water. In order to analyse the situation mathematically, we will introduce an x-axis and a y-axis and label the y-coordinate of point A y1 and the y-coordinate of point B y2. Clearly the x-coordinate of point A is 0, and we will label the x-coordinate of point B L. Finally, we will label the position where the light crosses from air into water x. Assuming that light travels with velocity v1 in air and velocity v2 in water, our task is to write down a mathematical expression for the time taken for the light to travel from A to B. To do this, we need to find the distance from A to x and then from x to B. Let's begin with A to x. Notice that I can form the following right-angled triangle and that the base of the triangle has length x, whereas the left-hand side has length y1. I can then use Pythagoras' theorem to calculate the length of the hypotenuse. Recall, Pythagoras' theorem states that the square of the hypotenuse is equal to the sum of the squares of the other two sides, and therefore I can express the distance from A to x as the square root of y1 squared plus x squared. I can then write down an expression for the time taken for the light to travel from A to x, since this will be equal to the distance divided by the velocity v1. What about the distance from x to b? Well, once again, notice that we can form a right-angled triangle with the top side length equal to L minus x and the right-hand side equal to y2. And therefore the distance from x to b is equal to the square root of y2 squared plus L minus x squared. We can now write down an expression for the time taken for the light to travel from x to b, which will be equal to the distance travelled divided by v2. And so we see that the total time taken is given by the following equation inside the box. We see from this expression that if we specify the start point A and the end point B, then the time taken is a function of the position x where the light crosses the boundary. What we now want to do is use this expression to find the position x which corresponds to the minimum time. So how do we do that? Well, one way would be to plot this function on a graph. If we plot the total time t on the y-axis and the position at which the light crosses the boundary on the x-axis, then we find the following smooth curve. We can clearly see from this plot that there is a minimum time, and so we can use the graph to read off the corresponding x position. Okay, but is there a way of finding an exact analytic solution using the expression for the time taken? Well, thankfully the answer is yes. All we need to do is find the point at which the gradient of the graph is 0. In other words, we need to differentiate t with respect to x and set this equal to 0. So let's do that. Okay, but exactly how do we differentiate this expression? Well, the answer is to use a trick known as the chain rule. To understand how this works, let's consider a simple example. Imagine we want to differentiate the following function, f of x equals 3x squared plus 2 all raised to the power of 4. One way of doing this is to define a new function which we will call g of x, which is equal to 3x squared plus 2. We can then write our original function as f of g equals g raised to the power of 4. Now the chain rule says that if we want to differentiate our original function f with respect to x, then we can write this as df by dx equals df by dg multiplied by dg by dx. So let's begin by calculating dg by dx. The 3x squared term becomes 6x and the constant term vanishes, and so we're left with just 6x. Next, let's calculate df by dg, in which case the g to the 4 term becomes 4g cubed. And so now all we need to do is multiply these two expressions together and we get 24xg cubed. The final step is to rewrite g in terms of x, and we get the final answer of 24x times 3x squared plus 2 raised to the power of 3. Okay, so let's now use this chain rule trick to differentiate our time function. To make our life easier, we're going to split the time function into two parts, which I will label t1 and t2. Let's tackle t1 first. We begin by defining the function g of x equals y1 squared plus x squared, in which case we can write t1 of g equals 1 over v1 times the square root of g. Next, we refer to the chain rule, which says that dt by dx equals dt by dg times dg by dx. If we then calculate dg by dx, we get 2x, and if we calculate dt1 by dg, we get 1 over 2 times v1 root g. If we then multiply these two expressions together, we get the following yellow expression. Let's now take a look at t2. This time we will define g of x equals y2 squared plus l minus x squared. In that case, we can write t2 of g equals 1 over v2 times root g. If we then differentiate g with respect to x, we find minus 2 times l minus x. And if we differentiate t2 with respect to g, we find 1 over 2v2 root g. If we then multiply these two results together and write our answer in terms of x, we find the following pink expression. We are now in a position to combine our results for t1 and t2, and if you recall, we want this to equal 0. We immediately see that in order for the blue expression minus the yellow expression to be equal to 0, these two expressions must be equal to each other, and so we can write this in the following way. So what exactly does this mean? To understand what this constraint is telling us, let's have another look at the ray diagram we drew earlier. This time, I will add a dashed line perpendicular to the water surface and label the angle of incidence θ1 and the angle of refraction θ2. Now we notice something rather remarkable. If I draw the following right-angled triangle around θ1, then notice that x represents the opposite side of the triangle and the square root term represents the hypotenuse. And so we see that sine of theta 1 is equal to x over the square root of y1 squared plus x squared. And so the left-hand side of our constraint equation can be written in terms of sine theta 1. Likewise, if I draw a right-angled triangle around theta 2, then we see that L minus x represents the opposite side, and the square root term represents the hypotenuse. And so we can write sine of theta 2 equals L minus x divided by the square root of y2 squared plus L minus x squared. And therefore we can re-express the right-hand side of our green equation in terms of sine theta 2. And so we see that the minimum time condition dt by dx equals 0 has resulted in the following equation: sine of theta 1 divided by v1 equals sine of theta 2 divided by v2, which is simply a statement of Snell's law. This is telling us that for a given value of v1 and v2, sine of theta 1 is directly proportional to sine of theta 2, which is precisely what Snell discovered. To make this clear, notice that we can write sine of theta 1 divided by sine of theta 2 equals v1 over v2, which is a constant. And if you recall, Snell discovered that if you plot sine of theta 1 against sine of theta 2 and calculate the gradient, you get a constant which we previously labelled n. And so now we finally see what n represents. N is referred to as the refractive index, and it represents the ratio of the speed of light v1 to v2. This is a remarkable discovery. To see just how remarkable, let's take a look at a couple of examples. If you recall, the experimentally determined value of the refractive index of water is 1.33, and so we now see what this means. This is telling us that the speed of light in air is 1.33 times the speed of light in water. Likewise, the refractive index for glass is 1.5, meaning that the speed of light in air is 1.5 times the speed of light in glass. And so you see one of the most powerful consequences of Fermat's idea is the prediction that if we measure the speed of light in water or glass, it will be lower than in air. This is a prediction of a completely different type. It is a brilliant prediction because all it required was the measurement of angles and the principle of least time. Armed with a simple idea, we can in fact explain a huge variety of interesting physical phenomena. For example, if you're driving down a road on a hot day, you might have seen a mirage appear in the distance, where it appears as if the road is covered in shimmering water, and yet no matter how hard you try, you can never actually reach the water. Well, we can now use the principle of least time to provide a simple explanation. Consider a person stood on the road. If it's a very hot day, then the road will absorb a lot of heat energy, and this means the air is very hot just above the road, but it's cooler higher up. Now, hotter air is less dense than the cooler air, and it's also thinner, and this means that light can travel faster through warmer air. Therefore, if we imagine a beam of light travelling from the sky towards the observer, the light can save time by curving down towards the road and passing through the warmer, less dense air. This is the path of least time. From the observer's perspective, they see the blue light as if it had emerged from inside the road, and hey presto, there you have it, a mirage. But why does light take the path of least time, and how does this connect to our modern understanding of quantum electrodynamics? Although the principle of least time was first discovered around 400 years ago, it was only during the first half of the 20th century that the result was fully understood in terms of the probabilistic theory of quantum mechanics. In the remainder of this video, I'd like to provide a simplified overview of how the principle of least time is related to probability amplitudes in quantum mechanics. Now, the first thing to appreciate is that quantum mechanics involves calculating probabilities. To see this, consider a photon of light travelling from point A to point B. In quantum mechanics, we begin by posing a question. What is the probability that a photon emitted from A is detected at B? The great thing about quantum mechanics is that there is a rule for how to calculate this probability. The first step is to consider a possible path taken from A to B and calculate the time taken for the light to travel along that path. Next, we construct a complex vector associated with the path known as the probability amplitude, which is proportional to e to the power of I theta, where the angle theta is proportional to the time taken along the particular path. Okay, but what exactly does all of this mean? Without going into too much detail, you can think of the function e to the I theta as representing an arrow, where theta is the angle made with the x-axis. Since the angle theta is a function of time, you can imagine this little vector arrow spinning as time flows. Now for each particular path between A and B, the arrow will spin by a different amount, depending on the total amount of time taken for light to traverse that path. As a result, the arrows corresponding to each path will end up pointing in different directions. Now the remarkable thing about quantum mechanics is that we can use the directions of the final arrows to calculate the overall probability that a photon emitted from point A will be detected at point B. To do that, we simply draw the arrows end to end, tail to tip, in exactly the same way that we would normally add vectors. We then find the resultant vector arrow by drawing a line from the tail of the first arrow to the tip of the final arrow. If we then construct a square with each side the same length as the final arrow, then quantum mechanics tells us that the probability is proportional to the area of this square. And there you have it, the rules of quantum mechanics condensed into 2 minutes. But what does this have to do with the principle of least time? To answer this question, let's return to our refraction example. Only this time, let's keep the rules of quantum mechanics at the forefront of our mind. The first step is to pose the question, what is the probability that a photon emitted from point A will be detected at point B? Only this time, point A is in the air, whereas point B is in the water. Again, the way that we answer this question is by considering every possible path between A and B. Now, obviously I can't draw every path, but you get the idea. We then calculate the time taken for light to travel along each path and draw an associated arrow. Remember, the amount of rotation of each arrow is proportional to the time taken along the path. If we do this for every path, then we will end up with a whole collection of arrows. And just as before, the final step is to add all of the arrows tail to tip. We then draw the final resultant arrow from the tail of the first arrow to the tip of the last arrow, and the overall probability is proportional to the area of the square formed using the length of the final arrow. Simple. But what has this got to do with the principle of least time? To make this connection clear, let's line up all of the little arrows again, only this time let's draw them underneath the curve which represents the time function t. The first thing we notice is that the arrows that are bunched around the minimum of the curve are all pointing in roughly the same direction, whereas the arrows far away from the minimum tend to be pointing in different directions. We can see this explicitly by referring to our graph. Notice that a small change in x corresponds to a big difference in time when far away from the minimum, and therefore adjacent arrows are likely to be pointing in different directions, whereas we see that a small change in x around the minimum of our function corresponds to hardly any change in time, and therefore all of the arrows bunched around the least time point in roughly the same direction. Now, if you recall, it's the length of the final resultant arrow that determines the overall probability. And if we look at our arrow diagram, we see that the main reason why the final red arrow has an appreciable length is due to the arrows that are all pointing in roughly the same direction. And these are the arrows that correspond to paths that are bunched around the path of least time, whereas the paths further away from the minimum tend to produce arrows pointing in different directions, which when added together tend to loop around and cancel each other out. And so we finally see the deep connection between quantum mechanics and Fermat's principle of least time. We find that the greatest contribution to the overall probability comes from paths that are very close to the path of least time, whereas those paths further away tend to cancel. And this is the real reason why light appears to be lazy. The detailed mathematical framework for how this works is known as quantum electrodynamics, and it represents one of the most successful scientific theories ever constructed. And it's a topic that I hope to return to in a future video where I will explore the mathematics in a bit more detail. For now, I would like to leave you with the wise words of one of the founding fathers of quantum electrodynamics, Richard Feynman. To those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty, of nature. If you want to learn about nature, to appreciate nature, it's necessary to understand the language that she speaks in. I hope this video has helped in some small way to reveal the underlying beauty of nature. Thank you for watching, and see you next time.